Okay, this time I'm intending to be talking more about the BJX core, as in the CPU core. Um, it's stuff related to the CPU core effort. So, yeah, basically major pipeline stages. There's IF, or instruction fetch, which fetches instructions from the I cache and figures out the instruction lengths. And, this is done during instruction fetch for reasons I will probably go into later. So then there's ID1, or instruction decode 1. This decodes the instruction words. This is the main actual decoder stage and stuff. Yeah, there's ID2, or instruction decode 2, or could also be called register fetch. This mostly fetches the registers from the register file and prepares the current operations to be executed. And there's execute 1, which which executes simple operations itself and submits values for more complex operations to the various other units. Execute 2 gathers the results from those other units back together and will block execution until those operations can complete, as in a pipeline stall. Then there's a write back stage, which stores back the registers to the register file. As noted, this is another depiction of the pipeline. So each cycle, one of these stages will initiate, and the other ones will follow. So, for example, first cycle would be instruction fetch here, and then next cycle would be fetching the next instruction, while the decode handles the instruction fetched here. And third cycle, then the second stage decoder is fetching registers, while the second decoder, or second cycle is decoding, and the third is fetching. This is, of course, why fetch kind of needs to figure out the length and stuff, because as it fetches here, it needs to figure out the next PC more or less immediately, so that the fetch can begin on this cycle, and so on. There's 3 of these here because at these stages the instruction will be split up into multiple lanes, each of which operate in parallel. During write back, the results are recombined and stored back to the register file. As can be noted, because the ID2 stage does register fetch, and the and for some operations the result wouldn't be generated until EX2. This does require interlocking. So if ID2 depends on register values that aren't written yet or aren't generated yet, then it has to effectively use interlock logic to add and off stages. So instruction fetch fetches a block of 64 or 96 bits. This depends mostly on the width of the core, a two wide core or can get by with 64 bits, whereas a 3 wide core needs 96 bits. Fetches those from the I cache. Logic from the I cache fetch may infer the length of the fetch instruction. So, as mentioned before, so PC needs to be advanced by next clock edge, and doing this in the ID1 stage would result in it being one cycle late. A past work around for this would be updating the PC based on the following set of instructions. So in this case, or in that case, like you would need to effectively deal with advancing the PC roughly 2 clock cycles in the future, which is kind of annoying because then you need to fetch more in order to figure out where like how far to update PC. For WEX that would be a bit more problematic, as then effectively instead of 96 bits you'd have to fetch closer to around 300 or so, which would be not ideal. So yeah, WEX fetch length covers the whole sequence. Sequence is analogous to a bundle in VLIW. Basically, multiple operations are fetched and fetched at a time, and PC is advanced for that whole collection of instructions. This will only cover one instruction if WEX is disabled. This is what would happen in scalar mode, or this would behave more like it would in scalar mode. In this case, the WEX hints are more or less ignored. So Decode 1 matches bit patterns for the instructions and unpacks them into a collection of fields. So basically, there's a major command, roughly 6 bits, a predication mode, that's 2 bits, bits for sub operation or memory access type, that's another 6 bits, and register IDs. These are also 6 bits each. There's only 32 registers, but one extra bit is needed for some internal registers and also for some control registers and other stuff. So that's where that comes in. And there's also a decoded immediate value. That's all these are per lane. So for a 3 wide core, you'd have three versions or 3 different commands and so on. But the decoded immediate value is a 33-bit value. This deals with the largest theoretical immediate that can be encoded directly, plus an extra bit for whether it could be sign or 0 extended. Or it should be sign or 0 extended. Actually, it's not sign or 0. In this case, it's more like 0 extend or 1 extend for negative. But basic idea, sign bit. It runs multiple decoders in parallel. As noted, for a 3 wide thing, it needs to use roughly 3 32-bit decoders. For There's also the 16-bit decoders and the 48-bit decoders, but only one of those needs to be run at a time because WEX only supports 32-bit operations, or yeah, 32-bit encodings. Instruction decode 2 fetches the contents of the various registers from the register file. As noted, yeah, this is for all the ports for all the lanes that need to be fetched. Things like immediate values and so on may be treated as registers here. Yeah, the register files supply the values to return for these registers. Basically, it's kind of a cheap hack of using effectively pseudo registers. Yeah. In this case, the decoder supplies a pseudo register, such as telling it to fetch the immediate or the current PC or other things, and the and the register file logic basically returns that as if it were being read from a register. This allows being able to handle nearly all the operations as register operations internally. Basically, don't need separate logic in the execute stages to deal with, like, say, versions that use registers versus versions that use immediates, because they're all treated like registers. This stage may also handle things like pipeline interlocks and so on. Basically, if the value won't be ready until EX2, but it's needed in ID2, then it will interlock in ID2, and the next cycle will basically just feed NOPs into the following execute stages. All operations in a WEX sequence or bundle are handled in lockstep here. So an interlock stall will be applied to all the lanes at the same. Yeah, interlock or stall will be applied to all lanes at the same time. Yeah, reasonably straightforward. Basically, it's not possible for the lanes to advance independently of each other. So everything happens roughly as it would in a scalar core, just 3 times as wide. This simplifies the design somewhat. Now, execute 1 will execute simple operations directly, and in this case the results are simply forwarded through EX2. These, in this case, due to register forwarding, it is possible to, for the following instructions, to directly use the results without resulting in an interlock. So that's kind of convenient. Where, yeah, ALU ops multiply and so on can be submitted to their respective units. The results will be gathered back during EX2. Basically this is because due to timing issues, mostly the ALU is done, or a lot of the ALU operations are done as effectively 2-stage operations. Yeah. Similarly, multiply is kind of expensive, so it takes 2 stages plus a number of additional cycles in order to perform it, and even then it's limited to 32-bit multiply, so not great. But such as timing on an FPGA. Yeah. So results are gathered back during EX2. Straightforward enough. This stage also computes the memory address and initiates a memory loader store. Yeah, so in this case, for example, LEA or load effective address instruction would itself be treated as a simple operation, whereas a memory load and store is more complicated. In this case, it computes the address and then submits it to the data cache, along with the command to load or store a value. The EX1 stage may assert a held register for operations it will complete in EX2, which may be seen by the interlock logic, as noted. If it sees a register is held and it needs the value from that register, it will trigger an interlock. Some other outputs may trigger an interlock. This would include writes to control registers and some other things like that. This is partly as a cost saving, or that's partly as a cost saving measure to avoid needing as much forward logic or other things like that for dealing with control registers, at the cost that writing to control registers is slower. But it's also rare, so that's a reasonable trade-off. During an interlock, the ID2 to EX1 transition simply produces knobs while the earlier pipeline stages are kept stalled, allowing EX2 to finish up the operation before advancing, as noted before. Once EX2 is done, then the operation is effectively done and the pipeline can continue advancing as normal. So execute 2 gathers up the results from the various units, outputting them to their respective destination registers. As noted, straightforward enough. May trigger pipeline stalls as needed in the case of slower operations or memory accesses, as can be noted. Yeah, these may take more than a single cycle, so yeah, so it basically asserts a hold value to keep the pipeline stalled until the operation can be completed. So stalls applied to all lanes at once, so the execution of a bundle will take the same time as the slowest instruction in the bundle or sequence. Terminology is not super consistent here, but yeah, as noted, everything happens in lockstep, so this follows from that. Write back gets the results of the execute stages written back to the register file. For WEX, this means consolidating the results from multiple write ports. This can be done via parallel register arrays for individual write ports, with multiplex logic being done on fetch, which selects a value from the array holding the current register value. This was one way to do it. It's kind of a little bit wonky, but turns out to currently be the cheapest option in terms of the widths I'm dealing with. From what I can tell, if I were going wider than 2 or 3, I'd probably need to resort to using discrete or discrete registers with multiplex logic on on each write port, but in this case that strategy is more expensive. Though for a three write port register file, that is relatively close to break even. Yeah, can also be done via discrete registers and with logic to multiplex the input values during writeback, or multiplex each write port into the discrete register. Yeah, not super straightforward to explain that much beyond this, but basically the partial reason for this is, as I had noted, if you try using a single array that's shared between multiple write ports just conditionally assigned to that array, then the cost in terms of FPGA synthesis effectively explodes. It works out for whatever reason to be considerably more expensive than just having a bunch of discrete logics with multiplex logic for each write port. So yeah. But but doing the multiplexing on the read ports works out cheapest for some reason. Not quite figured that out yet. For the multiplexing, in effect, like there would be a bit mask and stuff, where the bit mask bits would basically say which of the arrays holds the current most up-to-date version of each register. So when each write port writes, it sort of updates that bit mask, like to say which of the arrays currently holds the value. So that's how that works. Interlocks. An instruction in EX1 may sometimes not produce a result directly, but only after EX2 completes, as noted earlier. In operation, waiting in the ID2 may depend on the result being produced in EX2. Simply advancing the pipeline would result in off landing in EX1 and seeing a stale value for a given register. That is kind of why interlocks exist. Otherwise, one would need something analogous to delay slots between between adjacent instructions. So whenever a register was reading, you would have effectively delay slot until the value for that register gets updated, which would be kind of annoying. Interlock may need to insert a bubble into the pipeline to allow operations to see the intended values, as noted. We just need to pay for this convenience by losing a little bit of performance. Getting clever with the organization of instructions can help here, as if you can avoid using the register until later, then it won't trigger an interlock, and thus a little bit faster, but kind of harder when like Lex and Symwork get involved, or when the logic kind of doesn't really, or can't really be organized that nicely. So the execute and write back stages advance during a bubble, whereas the fetch and decode stages do not, because those are stalled, whereas execute continues to advance as normal. And as noted, the execute stages receive NOPs whenever the former stages are held, when the execute stages are not. Seems straightforward enough, so onwards. Forwarding. Registered results may be moved forwards along the execute pipeline and are stored back to registers during write back. So basically, yeah, that's how it works normally. Registers may be accessed from earlier in the pipeline before the values have been written back to the register file. Yeah, so basically, so EX1 or the EX1 stages, or EX1 stage, when it does its thing, it results in effectively temporary values for the registers to be written that are just sort of hanging out, that haven't been written back yet. When this is the case, if ID1 sees them, or if ID2 sees them, it'll just grab those values rather than grabbing the actual ones from the register arrays. Similarly, if EX2 has written the values and they're basically, or they can be fetched again instead of being fetched from the register arrays. So the register arrays are basically just the fallback in case none of the other two execute stages, or in case neither of the two execute stages have been writing the register at this time. Yeah, this is needed so that registers can be used directly after being modified by the prior instruction. As noted, this is separate from the interlock case, so interlock is for cases where it would need to stall, whereas forwarding is for cases where it would not need to stall, but it's being used so that we, don't need to stall. We'll see. So, WEX overview. WEX allows explicit tagging to be used to execute instructions in parallel. WEX sequences use the same basic representation or encoding as scalar sequences, but explicitly encode bundles of instructions which are able to be executed in the multiple lanes, similar to a VLIW architecture. This can be contrasted with superscalar, which needs to itself figure, or where the CPU itself needs to be able to figure out what can be safely run in parallel. In the case of WEX, it's it's given explicitly in the encoding. This basically means the processor doesn't need to figure anything out or deal with any uncertainty as to how far to advance PC or similar, but it does lead to the possibility that it can be given instruction sequences which aren't actually valid for the core. If this happens, it's kind of a problem, but it's basically undefined at this point. To be valid, the WEX sequence is required to exhibit correct behavior when instructions are executed both in sequence and in parallel. This allows the core to fall back to scalar execution as needed, such as an unsupported profile or lack of WEX support. Basically, because both 2 wide and 3 wide cores are a possibility at this point, Um, there needs to be logic to deal basically with the case such as the code was generated for a 3 wide core but only executing on a single or on a 2 wide core. In this case, it would need to basically cause WEX to be disabled and fall back to scalar execution. However, 2 wide code can be run on a 3 wide core without issues, so that is something. This also allows a potential superscalar core to effectively ignore the WEX, since, as noted, superscalar is a lot more expensive but allows the possibility of more aggressive optimization. However, it would not necessarily be operating under the same rules as the WEX encodings, so we would want to be able to effectively ignore the WEX hints and be able to treat the instruction sequence as if it were a normal scalar sequence. So this is allowed for, with the restriction, as noted, that the sequences need to be correct in both cases. So the actual expressiveness of the instruction encoding in this case is more comparable to that of an in-order superscalar, though albeit just with explicit hinting during or in the instruction encodings. Register ports. So each lane has 2 read ports and a write port. If all lane, but as noted, a lot of instructions have 3 registers, and some instructions can read from all 3 registers. So this is a special case. If all lanes are used, the results from the values read from the destination registers will be implementation dependent and will typically alias with other register ports, as noted, because each lane only has 2 dedicated ports. So in this case, we have to typically use the ports from the final lane for the prior lanes, and if we're using all the lanes, then we have a problem. And this particular scheme works with both 2 and 3 lane designs, but kind of falls on its face for 4 lanes and above. So if fewer lanes are used, each hop will behave as if it had all 3 read ports available. As noted, this would be a single wide instruction on a 2 wide core, or a 2 wide bundle or sequence on a 3 wide core. Generated code should not depend on specific register aliasing behavior. Again, that's because that would make a horrible mess and limit the ability to run on different cores. So so basically this is a don't do this case. Note that a scalar core will have 3 read ports and 1 write port, rather than 2 read ports plus 1 write port. So this is obvious enough. Basically it means that the 2 wide case only needs 1 additional read port versus a scalar case. Hence also why there's less of, partly also this is why there's less of a jump between the 1 to 2 cases versus from 2 to 3, but that and some some non-linearities in terms of cost and other things like that, but yeah. So most operations fit nicely with the 2 read plus 1 write configuration. So for example, adding two numbers only needs 2 source ports and 1 destination port, and likewise for most other operations. The main exception here is memory store. It's because memory store effectively needs two operands to generate the address, and the destination port is basically used as a source port for the value to be written back to memory. Partial result of that being that one is quite limited in terms of what they can run in parallel with the store in a 2 wide core and stuff, whereas for a 3 wide core most operations can be run in parallel with something like a store. Though with the exception of other memory hops, because there's only a single lane interface to the data cache, so only one loader store at a time in this instruction set. This could change later, but it'd probably be different profiles or similar. So yeah, it is possible I could later define a profile like that, but we'll see. So register ports naming. So for the 2 wide case, there's 4 read ports labeled S, T, U, and V, and 2 write ports labeled M and N. And for 3 wide, it's similar, just with 6 of them, and the X and Y ports are for the 3rd lane. And an additional RO port is added as a 3rd write port. These are not quite the same as for the instruction labeling, but they sort of map straightforwardly enough. So so lane 1 would map to S and T, lane 2 would map to U and V, and lane 3 would map to X and Y with the restrictions. So in the 1 wide case, S and T are used as the first 2 source ports, whereas V is used for the destination port or destination read port, and stores to R via the RM port. In the 3 wide case, it's similar, just using port Y instead. This allows lane 1 and 2 to use all of their read ports, whereas it's lane 3 that's sacrificed. So in the 2 wide case, yeah, 2 operations are run in parallel. They only have their first 2 read ports available. The the destination register will read an undefined value in these cases. So if like you try running something in parallel with a memory store, it's not entirely defined what value will be stored to memory. That's how that works. In the 3 wide case, as noted, all the destination register ports are whereas in this case you can run in the 3 wide case you can run 2 operations in parallel with the memory store because it has its needed 3rd port. But in the 3 wide case when running all 3 instructions. Then the destination ports don't or have undefined values, as noted. But basically works. In invalid combinations of operations, the registers may alias in an implementation defined manner. That is, as noted, because effectively in the current implementation, the handling of the third register port is via an aliasing mechanism. So you know, the third register ports or third registers just get a copy of some of the other register ports. Yeah. An implementation is neither required to detect nor trap in these cases. This again is because of cost. If it detected and trapped, then it would be, that's, well, part of what you'd have in a superscaler that is being avoided here. So there's other stuff, but yeah, it's part of it. And not detecting is the cheapest route, so that's why it's done this way. If operations are performed which are not allowed in a given lane or within a given combination of instructions, the resultant behavior will be undefined. An implementation is neither required to detect nor trap in these cases. More or less, yeah, about the same as above. So trapping or detecting and trapping is expensive, so we don't do it for this. Yeah, pretty much. Constant and immediate values. BJX2 primarily uses one of several mechanisms for expressing constants. There's immediate values, which are typically small and fixed size. If we're doing 32-bit instructions, as noted, yeah, since the number of bits in the instruction is fixed, there's only so big of an immediate that can be handled directly in the instruction. So different instructions will have different size immediates, but they're, as noted, typically small and fixed size. In the majority of cases, though, instructions can get by with small fixed size immediates, so that's why they're done, or why they exist. But these are not always sufficient, so other cases are needed. A dedicated DLR register, or R0, exists, which is basically an implicit destination and or source register for some various instructions. These are often used when an immediate can't be encoded directly. Basically, in the assembler stage, and also indirectly by the compiler, it sort of pretends that it can use more or less any size immediate with an instruction which can accept an immediate. Since this is not actually the case, if it doesn't fit, it loads the value into DLR instead, and uses a register as the immediate. This does basically work. However, both R0 and R1 are effectively taken out of the main register case and considered as special purpose registers. This is partly because they're used for constant loading and for some special stuff, and also because some amount of like other machinery sort of updates them via side channels, so they're special and stuff. Yeah, in terms of the encoding and stuff, yeah, R0 and R1 are also used to encode the PC relative and GBR relative memory access modes, so so effectively can't be used directly as memory bases either, and thus special. These are often used when an immediate can't be encoded directly, as noted. Load immediate instructions. These would be LDIZ or LDIN, and yeah, for example, they could load a 16-bit zero extended value into a register, and it's just, yeah, the destination register equals or is assigned the immediate's value. So there's a 0 extended version and a 1 extended version. So this effectively means you can load 17-bit values directly into a register via 32-bit forms. There's actually 48-bit forms that extend that to loading a full 33-bit immediate, but as noted, that is effectively incompatible with WEX due to WEX depending on 32-bit encodings. So, yeah. So one slight compromise with WEX is that it is limited to slightly less efficient handling of larger immediates, but yeah. So load shift instructions, which basically shift the destination register left by a certain number of bits, and then just sort of tack the bits into the low part of the value. These can express arbitrary constants without needing to resort to a memory load, which is slower and more awkward for code generation. So basically, with these, you can load an arbitrary 32-bit constant in 2 instructions, and an arbitrary 48-bit constant in 3 instructions, and an arbitrary 64-bit constant in 4 instructions. Well, say 3 or 4 instructions is while using 3 or 4 instructions is more instructions than, say, if you used a memory load to do it. It does work out faster because these operations can be done effectively in a single cycle, whereas memory loads would take more cycles, depending on, like, whether or not there's a cache miss or other things like that, and even in the best case, they're still multi-cycle operations. So, yeah. Similarly, do the traditional RISC style route of using memory loads is rather inconvenient. For example, you typically will end up dumping blobs of constants right in the middle of the code stream, which is kind of a problem for things like branch length optimization, because in one attempt to generate it, it might dump the blob of constants in one spot, so you need to branch over in one spot, and the branch links might start being specialized for that, but then because the branch links have changed, then you have, or then it doesn't necessarily need to stick the constant blob there anymore, so it might in turn go and stick the constant blob in another place, and since those ones weren't previously being adapted for there being a constant blob there, then your branch links are no longer valid, and that sort of thing is problematic. So one needs their constant blobs to either remain in a fixed place, which is problematic due to distances and so on, or they or something else, or they need to deal with branches that are less efficient than they could be. So that would be, for example, always using 20-bit branches where 8-bit branches would be sufficient. Loading and shifting into place, which is 2 operations in BJX2. This is a single operation in ARM, but BJX2 doesn't really have that specific combination. It is theoretically possible I could add a single op for doing this at some point, but it doesn't exist for now. This is useful for constants where all the low bits are zeros, as noted. Yeah, so for example, if you're loading a double precision value, in many cases, since most of the low order bits are zeros, you could use a narrower constant say 12 or 16 or 24 bits depending on what's available, and then just sort of shift it all into position via another instruction. So allows in many cases things like loading double precision values to be done within 2 operations, and similar for a lot of constants and other things like that, following a similar format. These are semi-common, though not quite as common as the value not quite as common as the cases where the value is small and fits in a small immediate. The load shift instruction is noted as useful in case the load shift instruction sequence is useful in cases where the constant effectively has contents in all of its bits and can't be expressed via more compact trickery. So this is more the general case fallback, but it does remain fairly useful. Well, at least fairly useful if considering the main alternative is memory loads with their associated problems. But if you were to try to do similar in something like ARM, you would effectively need around 3 times as many instructions or so. Thinking. No, it's actually about twice as many, because you'd have to basically do a sequence of shift operations and a sequence of add instructions in order to build the constant, which is much less convenient because it's twice as many operations in that case. GPR floating point, or GFP, BJX2 in the F profiles, but this will probably be extended to include the A profile and similar as well. Provides a reduced cost FPU, mostly via using GPRs rather than dedicated FPRs. So GPRs are used for the holding the floating point values, and nominally each register holds a double precision value. You can hold single precision values, but you can't directly do arithmetic on them with this with these instructions. So reuses GPR operations for load and store and so on. This is itself mostly a cost-saving measure. So no need for dedicated float or double load or store operations in this case, because you can just use the double and quad word operations instead. Though as a cost of that, it needs to use explicit type conversions to load and store 32-bit floats, so it doesn't come free. There are some dedicated 16-bit encodings for some of this stuff to reduce cost in these cases, because initially I was just using 32-bit encodings for all of this, but that did some not good things to code density, particularly with like programs like Quake and similar, which were considerably larger using the GFP instructions than they were using the dedicated FPR instructions. So, but I've got it a little bit better now, mostly by making the conversion between float and double be able to use a 16-bit off and similar. So has a fairly limited range of operations, namely add, subtract, multiply, compares, and type conversion, and similar. There's also abs and neg, but those are basically just simple bit twiddly offs. So so things like divide, square root, and so on are done in software. So basically whenever one tries to divide two floating point numbers, the compiler will effectively spit out a function call, and that will in turn use the good old Newton-Raphson iteration to do the divide magic. So, but basically works and isn't too unreasonably expensive. Similar applies for square root, but in C, square root was an API call already anyway, so it doesn't make a huge difference for C. However, never mind if the IEEE standard had defined square root as being a built-in operation. In this case, it doesn't apply. It excludes some features which rarely have much significance. These would be denormals, which are basically treated as zeros in the BJX2 FPUs, and also excludes things like flexible rounding behavior and so on. Pretty much no real code in C ever really messes with that anyway, so it's kind of moot. Denormals could theoretically have a very slight effect on in some cases, but typically the result is negligible, and treating them as 0 has little or no real effect on the results seen. Similarly, things like rounding behavior are pretty insignificant, and it's cheaper to just hardwire it to being round to nearest for the normal floating point operations. So this is not strictly IE or IEEE conforming, but should still be usable for most things. Yeah, obvious enough. Should be, or can be noted that basically ARMS, Neon, and Similar does mostly the same thing in these areas. So it's not like it's too unusual or unexpected. And the actual representation of the float and double values remains the same as in the IEEE format, so the differences are largely invisible. Yeah. I think I've mostly covered this, but yeah, as noted, yeah, FPU still isn't free, but could be worse. So, GSV, GPR-based SIMD. This implements some packed word and D-word operations via GPRs and aims to keep the cost and complexity relatively modest. A goal here is to limit the number of new instructions as well as the complexity of the machinery needed to support them. As noted, it is a pretty common problem with SIMD ISAs to add an excessive number of instructions trying to basically address every possible possibility, and even then it's still kind of hit or miss, and adding a lot of additional complexity, like such as like operations performing saturating arithmetic on the various elements for the various sizes, and sometimes with implicit or with various format conversions and similar thrown in as well, such as in the case of Neon. And preferably I wanted to avoid most of that, so it aims for relatively minimal set of features that can to some extent where possible be implemented on top of the existing ALU mechanisms. So for example, the ALU internally is mostly using carry select adders and subtract units, which do perform the operations internally as a number of smaller 16-bit operations, and then combine the results afterwards. And in the case of a packed word SIMD, what you can do is instead of like, you know, using the combined results from the combined like double word or quad word results, you can just sort of grab the individual word results and use those instead. Just say like use the word results where you assume that all the carry ends are zeros and similar. This, it's basically cost saving, and more complicated things like saturating arithmetic and similar are not currently supported in GSV. Yeah, it does not directly support packed byte operations, again partly because that would add some additional cost, and not going to bother with that. Does indirectly support packed byte, but mostly by being able to convert from packed byte to packed word and then perform the operation, then swizzle it back to being packed byte again for storage. That should be generally sufficient for a lot of uses, so yeah. And still probably better than having to do it all with scalar operations. But yeah, since it's using GPR operations, it can also be combined some with some pseudo-simmed strategies as well. And this can also reduce cost and the number of operations needed. Mostly reuses existing integer operations and stuff. So all the memory store, load and store, and all that stuff is basically the same as it would be for normal scalar code, or for scalar integer code. Does not exist as a disjoint simmed ISA. Similarly, same registers and mostly the same operations in both cases. And yeah, registers remain as 64 bits. I currently have no intention of going the route of having increasingly ever larger simmed registers, because that's kind of lame. So instead, my current plan is just reuse the 64-bit GPRs and leave them as is and mostly call it good. And by itself, GSV will not support packed floating point types. Similarly, yeah, it is possible to sort of do packed floating point via the GFP, via the former GFP extend, or like instructions and stuff. Since you're dealing with since you're dealing with like GPRs, and there's some overlap between what you can do with the GSV operations and the GFP operations and so on, that it allows effectively just pretending like you had packed floating point types, though without some of the implied performance advantages or anything like that. But it is at least arguably better than using discrete memory loads and stuff for each floating point element, which is what you'd have to do, say, if you were just passing a pointer to an array of floats or something, which is the more traditional route. So it's kind of a compromise in that sense, but there is another extension I'd called GSVF, which would add additionally support for packed half-word operations and sort of packed reduced precision floating point 32 values, but that's kind of a bit more uncertain at this point. For the packed 32, for the packed float values, in that case, the precision would be a bit lower, mostly because internally the FPGAs only have 18-bit inputs and similar for their DSP units and stuff. So it would be using effectively an 18-bit Manteso rather than the full 23 bits and so on. So less precision. For some applications, that would probably still be useful, because it would be equivalent mostly to operating with 32 bits floats being shaved down to 24 bits or similar. So yeah. And still technically a little bit higher precision than using half and with a larger exponent range. So yeah. In the mock-up I did before, it could, just sort of handle both cases more or less via the same logic internally, just with some slight difference in terms of how they unpack and repack the low precision floating point values. So yeah. So yeah, that's all my slides for now. And do I feel like going on at this point? Just going to see if there's anything worth pointing out in my code. So okay, so a 3 wide, like a case for special purpose registers, or this is basically how all the registers would work in the discrete register case. Namely, there's a module which accepts the 3 write ports and has a combined register ID and value and stuff. The register ID is mostly a self-identification for which register we're dealing with, so it's typically a constant, and there's a input value useful for side modification, which is common for special purpose registers, and a hold input for whether or not the pipeline is held. In cases where the pipeline is held, we typically don't update the registers until after the pipeline is no longer held. That's how that works. This feature here basically helps limit garbage getting written into registers, which can happen sometimes if we don't avoid writing stuff back when it's held. Yeah. So the way it works is we just check which of the ports is equivalent to the current register, and if any of them are, then the next value for this register becomes the whichever one is selected, or the input value if it's none of them. In the case of a simple register, with no side channel modification, this would just be a loop, or looped back from the output value. So output value goes directly back into input, causes it to update in the loop. And similarly, on the clock at regis, if it's not held, then it updates the register. And if it's held, well, then nothing happens, it's ignored. So that's how that works. Anything else? So 3-line decoder, or 3-lane decoder, produces ST and M, U, V, and N, and X, Y, and O, and it's about 423 lines for this main module, and so just sort of invoking the other decoders for the other parts of the operation and stuff. In this case, we just sort of hack off the parts we're interested in for the sub-decoder and fill the remaining bits with undefined, since, you know, we don't care. The FZ decoder handles the 32-bit operations, and technically it could be, you know, just given 32 bits of input, but it's however the magic works in Verilog land. Similarly, the base decoder probably doesn't need, like, you know, 63-bit input or bits of input when it only uses 16, but yeah, VIF-Auto just sort of prunes that out anyway, so basically works. And a bunch of actual work that's going on here is logic to basically figure out what we're looking at. So whether we're looking at a predicated op or predicated op or a larger op or just a 16-bit op and stuff, and then also does the same things for the next instruction, mostly to detect if it's 3 wide, and then it figures out, okay, is it a WEX operation, and is WEX even enabled right now, and stuff. So if it does, if we have WEX here and it's enabled, and we have WEX here, then it's enabled. So then after that, if it's a 48-bit op, well then the first lane gets the 48-bit op, and then the other lanes just sort of get some duplicated values. These are, just get some duplicated values. For example, for the third register port, it's duplicated onto the relevant lanes from the relevant positions in the other lanes. And if we have all three, if both instructions are WEX, that means we're dealing with a 3 wide case, and all 3 lanes get the output of their respective decoders. And so 2 wide case, as noted, both lanes get their respective decoder outputs, and the third lane just gets the third register from each of those first 2 lanes. This here works because, as noted, the register lanes or register ports are effectively just aliased in these cases. So we use the third lane as the inputs for the third register for these other 2 lanes. And as noted, the value is just duplicated and gets where it's needed. Single wide likewise. And 16-bit ops are similarly likewise. So 16-bit ops may use 3 register ports, and that's kind of expected. All sort of decoder magic. All the mechanisms are internally. And this last little bit deals with predicated ops. So if the operation is predicated, then we update its execute mode depending on its predication bits. So DZA basically means is it a predicated op, and DFA basically means is it on the false path. As noted up here, the false path, the false path is used by WEX. So basically the false path is also used as the WEX bit when not dealing with a predicated op. So basically, if we got false path, but we're not looking at a predicated op and WEX is enabled, that means WEX op. But if we are looking at a predicated op, well, that means it's the predicate flag. So that's how that works. Basically, a technical limitation at this point is that it is not possible to use WEX with predicated ops either, but this isn't too huge of a loss since those two cases are usually mutually exclusive. Namely, that WEX tends to happen in terms of larger, more winding collections of expressions, whereas predicated ops generally happen in dealing with small isolated branches, which only do simple tasks like assigning a register or assigning value to a variable or similar. So the two use cases tend to not really occur at the same time, so it's a reasonable trade-off that it's not encodable either. Though in an ideal world you could possibly be able to encode both, so you could have your small branches be stuck in with a bunch of WEX code and not actually need to branch or not actually require a branch in the CPU core, because branches are also expensive. But well, you can stick like predicated instructions in the middle of a bunch of WEX code, but they just won't do that much interesting. They can avoid branches, but they'll just run sequentially. So tried to think of workarounds, but not thought of a good workaround or encoding for this case yet. So that's how it stands. As noted, also in the case of WEX, lanes 2 and 3 tend to use alternate versions of the EX1 and EX2 stages than are used in the first lane. This is primarily to deal with the logic, or what can be done in the second and third lanes being considerably more restricted than what can be done in the first lane. So the other lanes are not allowed to perform branches or do memory operations, or to do other things which would update the values of the SR flag bit or other things like that. So because of this, the SR.T bit and so on. So because of this, they're well, mostly empty. The only things they can really do are ALU stuff. Yeah. And well, also shifts, but shifts aren't visible in the EX2 stage because those ones happen directly in EX1. So if you go here, EXP, or in EXP1, yeah, shift operations still have logic because they're single cycle operations. I think at one point I'd considered making shifts be 2-cycle operations, but ended up not doing so because they're not slow enough, whereas things like adding two numbers and similar are slow enough to require 2 cycles. Things like AND, OR, and XOR could theoretically be done entirely in EX1, but aren't done so, mostly because they're a lot less common than things like add or subtract. So there wouldn't be as much advantage for doing so. Kind of kind of makes sense that you'd need them to be a lot more common in order to justify the added complexity of having a special case for them. So they're done roughly along the same path as add and subtract, and thus take both execute stages. So, or at least for now. And multiply is just, way too slow, and also doesn't exist in the secondary lanes. It could exist, but it would require well, 3 copies of the multiplier, and the multiplier itself pretty expensive. So there's only one of those. I could potentially have some low precision multipliers that are available in all 3 lanes, but given most of the time if you're multiplying stuff, you kind of expect to have a full 32-bit multiply. That would be kind of less useful, because the second and third lane multipliers would probably only be like 16 or 18-bit multipliers, and thus less useful. So what else? So logic for predicated ops is relatively straightforward. So if there's a branch flush bit which is used as one of the inputs, and the operation mode which is used as 2 input bits, so if they're all 0, well, that means it's a plain unconditional op, so it's enabled. And if the mode is, or the what mode is 1, that means it's never executed. So 0, 2, and 3 with no flush bit basically mean it's a predicated op. So the sr.t bit is used to select, well, whether or not it's executed, and if the flush bit is set, well, then it's not enabled because it's being flushed, or the pipeline is being flushed, such as due to a branch or something, so we don't execute then. And if it's enabled, then the command is fed through. Otherwise, a NOP is fed through it. Then if it's a NOP, well, nothing happens. And similarly over here, nothing happens during a NOP, But if it's something other than a NOP, well then something happens. Unless it's an instruction that's not allowed in these lanes where nothing will happen. It's basically like a NOP. Yeah, in the current CPU, or in the current core prototype, basically it will not detect like operations that aren't allowed in that lane, but for the most part, if an operation isn't allowed in that lane and it's encoded that way, it'll behave as if it were a NOP. So it's a case of probably good enough. Or I could, add some slightly different logic and make it do a fault or something. But something or another. Case of to be resolved later, probably. Yeah, to be resolved later, like maybe make invalid instructions fault or something. Currently they don't, because this prototype is kind of, well, still a prototype. And some logic is still needing work. But in terms of what can it do, so we'll see if it's still in a working state. Oh yeah. This is, running off the Verilog simulation, so it's does its thing of, reading from a FAT32 image and starting the boot process. This is about the stage of workingness in the current core prototype. And what is the current cost for in Vivado? Well, so this is for the 3 wide core in the Vivado, and its cost is currently roughly around 20,000 LUTs. So with with almost 2,000 elements used up for LUT RAM, which is not too unusual. This is mostly the register, mostly being used for the register file on the L1 caches. The current prototype uses uses comparatively rather small L1 caches, but this works mostly it's for timing reasons. And 8,000 flip-flops, yeah. And I have little idea why FPGAs have so many flip-flops available. So there's, twice as many flip-flops as there are LUTs, but, in terms of pretty much all Verilog code I've written, you need far more LUTs than you need flip-flops, so I don't get it. BRAMs. Well, yeah, using about 35% of the total BRAM. That's for the combination of L2 cache and displays frame buffer and similar mostly, so yeah. This is for an Arctic 7, which Nexus A7, well, yeah, Arctic 7 with 100T, so considerably like a bit bigger than the Spartan 7 ones I also target, so it only uses like, you know, a third of the Arctic 7 in this case, but it would have, you know, used pretty much the entire budget of the Spartan 7 of, yeah, all the Spartan 750. And this would also similarly not actually fit on the Spartan 725, which another target. But so yeah, for this, for the S725, would, yeah, that would use a scalar core rather than a 3 wide WEX core, but previously it fits, so that works. And well, you'd also scale down the BRAM used in that case. Like, you wouldn't be all using a, or you wouldn't all be using a 64 L1 or L2 cache, and like you wouldn't be using a 64K L2 cache and frame buffer and stuff in that case, because, you know, that's eating up like 128K of memory, and that's a bit steep. On that, the A7 could actually probably afford a full 128K I cache as well, or actually L2 cache as well, but yeah, that's not what I'm doing right now. So yeah, the A7 is, or yeah, the A7 100 is quite a bit bigger than the S750, so that's mostly what's going on, why it's at 30%, because I was previously writing this thing for the S750, and but I got a bigger FPGA mostly because it came with more nifty ports and stuff. So VGA port is nifty, and SD card slot is nifty. Would otherwise have to have gotten like some PMod modules for the RDS7 or something at some point, but not done so. And DSP units, well, this current 3 wide WEX core is currently using 17 DSPs out of 240 possible, but not sure what the 240 DSPs are for, unless maybe they're expecting people to be doing stuff with like a whole lot more multiply or something, but mine doesn't do that much multiply, so doesn't use DSPs. Or doesn't use so many DSPs. So yeah. BUFG is 2 currently because currently that's mostly because I ended up giving up on clocking it at 100 megahertz internally, due mostly to timing being a pain, so drop the CPU core down to 50 megahertz, which means 2 clocks, so 2 BUFGs. So yeah. And so this is basically what the 3 wide WEX core currently looks like in terms of FPGA resource usage. So what is this? Yeah, RAM block for the ROM, and looks like L2 ROM. And SRAM. So yeah, in this core there's about 32K of space used up for the boot ROM and similar, and another 8K used up mostly as a boot time SRAM. And that's also used for things like the stack during interrupt handlers and other things like that. So basically for that you want for interrupt handlers you want memory that's effectively always in cache and never paged out. So that's what the SRAM is for. This means it can handle interrupts in a potentially timely manner. And more block RAM. More ROM. Yeah. Always that fun. Good old DSP. This one. Yeah, that's used for the VGA module. The VGA module currently is kind of a hack in that I originally wrote the display stuff for NTSC output, but sort of hacked it over into VGA output, and internally it's still like trying to output its display as YUV, but does sort of a really quick and dirty hack conversion over to RGB at the last second, and then it outputs RGB because that's what VGA wants. Future redesign effort in that front would probably be making it all use RGB internally and stuff, rather than, you know, potentially in some cases having to go from YUV or from RGB to YUV then back to RGB again for no good reason. Also, reducing the amount of conversion stages in that case could probably make the output look better or something, but given I've not actually even run this on real hardware yet, it's probably kind of a moot point at this point, but to be addressed later. Always block RAM fun. And zoom in really far on here and see the individual LUTs and similar. So LUT, and a carry. So yeah. Yeah, this one's a LUT 6, but no carries. So this one is using a carry, so that means it's adding a 4-bit number. And well, this one has 3-bit LUTs on it. So 4-bit LUTs and a carry. So yeah, always the fun of this stuff. So yeah, 5-bit LUTs on that one. Yeah. All the stuff we don't actually deal with directly in Verilog. zoom out too far and you just see generic blocks with no individual parts, but here you can see the parts. Not that this is particularly relevant or anything, but and all the parts I'm not using. Yes, the thing is, I guess the thing is like these Matrix 7s or Arctic 7s have a bunch of inherently parts in them that aren't generally used, aren't really used by most designs, and are kind of what they left out when making the Spartan 7. But yeah, all this like high bandwidth transceiver stuff and similar. So the Spartan 7 lacks them, but most like people trying to do CPU cores or similar wouldn't use them anyway. So yeah, they took them out to save costs, which is kind of funny if one considers it. Like if you actually bought the FPGAs directly, there's not really like a whole lot of difference for similarly statted S7s versus A7s, but and for whatever reason the A7 seems to be not clocked quite as high or quite as easily as the Spartan 7 for reasons I've not figured out. Like, theory goes, they should be entirely equivalent, but there seems to be at least some small difference in timing there. Similar goes for the mystery of why there's any difference in terms of look cost between like basically using doing like a 256 bytes for an L1 cache versus 1K byte when you know, the LUT RAM is the same, or basically the same, and always uses 6, or yeah, the LUT RAM, yeah, the LUT cost should be the same because the LUT elements always take 6 inputs, but there seems to be a slight difference in terms of cost between them for some reason. But FPGAs work in mysterious ways sometimes. Yeah, various units exist, so as noted. No, not a huge cost between these ALUs in terms of LUTs, and well, these two are the same type of ALU, but the third lane one is more expensive than the second lane one for whatever reason, despite being otherwise entirely the same logic between them. So yeah. FPU has an add subtract unit, which is kind of expensive, but that's how FPUs go, and a compare unit, which does equal and greater than compares. Can't, yeah, for subtle and annoying reasons, you can't just directly reuse the integer compare logic for floating point values because of little subtle details like the expectation that nans do special things and so on. So if you compare equal with nan, it's always supposed to return false, whereas a simple integer compare would return true if the bit representations are equal. And similarly because floating point values compare different, or are you sign magnitude rather than 2's complement, the greater than logic ends up being different as well. So in this case, they end up with their own dedicated compare unit that's separate from the integer compare unit, which is maybe or maybe not kind of wasteful, but either way. Multiply, well, FPU multiply, that's also kind of expensive, but yeah, they are double precision. A single precision FPU would be cheaper, but yeah. But yeah, I'm using double precision as the main FPU because a double precision FPU can also do single precision, and it's more generally useful. Because if you only have one, then you kind of need the higher precision one. And simply doing single precision FPU would actually turn out to be insufficient and result in lower performance even for something like Quake or similar, since a lot of things it does, like mathlib operations and other stuff like that, would basically be slow due to needing to fall back to software emulation or similar. And if you can avoid software emulation for floating point, then you kind of want to. Except in this case for integer or for floating point divide, but in terms of functionality, there wouldn't actually be a huge performance difference between doing it in software and doing it in hardware anyways, since the Newton-Raphson stuff is kind of expensive either way. So it's, do you spend 80 cycles for a state machine inside the FPU to do so, and then spend like several thousand lits for the privilege, or do you spend maybe like 100 cycles to do it via Newton-Raphson in software? It's like, well, yeah, the cost in terms of cycles isn't that much different, so may as well go for the software route in that case. Similarly, there's integer divide, but I could make that faster, but it's not enough of an issue to justify it. The great to do would be like, well, like to do like re-add the super H style like partial division operations, because those things were actually surprisingly fast for what they were but just haven't done so because integer division is still kind of uncommon and generally expected to be really slow, so it doesn't matter that it's kind of slow. At least kind of slow because it's being done via like a shift compare divider as is. So yeah, shift compare divider in software. No hardware divide, because hardware divide is, well, expensive. And it would be a big ugly and hairy state machine, so didn't bother with it. And as noted, there is no microcode in BJX2, so this is all direct logic and all internally 64-bit, except for the address bus, which is, I've just gone with 32-bit addressing again to save cost. But at least in these profiles. The A profile would have like a 48-bit address space, but yeah, that would probably be mostly just at the MMU for now, because not much point in using a 48-bit physical space on FPGA dev boards, which would have no real capability of actually being able to use such a big address space. Would make sense on like a desktop or something, but that's not what I'm doing here. And similarly like when running small programs on an FPGA dev board, when I'm only having really enough RAM to justify 32-bit address space, it's kind of pointless to have, a full 48 bits on that. So partly why different profiles exist. And okay, so what happened here when I was not looking at it is, so got through the boot process in the Verilog simulation, and then it started booting up Doom to do its Doom thing, where his Doom gun did the fat thing, has a bug, not gone to figure what's going on there yet, tries to probe for the heretic wad, because is it doing heretic? It doesn't know. Oh yeah, and because I hacked this version of the Doom engine to try to fake or pretend to be heretic, so that's why it does that. And then it basically hits an instruction it doesn't know how to decode. Wait, I'll have to find my listing and see which instruction that is. It's in the 3 block. Okay. It's a move T instruction, so copy sr.t into a register, but seems I don't have the logic in place for decoding that form of that instruction, so makes sense. No. So 32-bit form of move T. sending it over to R12. So yeah, it's not encoding it that way because it's yeah, not encoding that way because of actually needing to use that size register, or needing to use a large register, but the 16-bit encodings can handle all 32 registers for these operations anyway. It looks like it was probably because, or guess is probably because it was in a area where WEX was expected. So in areas where it can potentially do WEX, it encodes everything as 32-bit or 32-bit instruction forms, and yeah, encodes it as 32-bit instruction forms, and then it sees what it can shuffle around and put in parallel, or put in, and which operations it can put in parallel with each other. So yeah. So that's how that works. But and can tell by looking at it that it's also a lane 1 encoding, so that's not a surprise, too much of a surprise there. Oh yeah. Oh, here's a where I'd exited the emulator as well. So Doom is currently being built with some use of WEX forms enabled. So yeah, can be noted, for example, this add s is being run in parallel with this 0 extension operation, and that's in parallel with a move operation. And this is a WEX3 form here, so 3 wide, and some of these other ones are 2 wide cases. So add in parallel with an and an add in parallel with a constant load, and then this other and by itself. Because it would depend on the value from that constant load, so it can't be run in parallel with other stuff, and then it produces a value needed by this following up, so it couldn't be run in parallel with these. Yeah. So yeah, in cases where it's not using WEX, that's because in these cases where it's not running them in parallel, it's because there's actually a dependency chain between these instructions, so can't do that, and there's probably nothing else to put in between them useful right now. But yeah, at least for this sequence of instructions, it's doing moderately well. So it's a good chunk of these encodings are WEX encodings. So yeah, as noted, the compiler does try to shuffle the instructions around into an order where it can actually apply, or actually run things in parallel. So yeah, the logic that would be otherwise done in a processor to try to do something like out of order superscalar or similar is basically applied in the compiler in this stage. It can't do anything speculative with memory or anything like that. But the processor core in this case is far too dumb to be able to deal with any kind of speculative memory stuff anyway, so yeah. So no speculative memory stuff and no speculative execution because, well, it's, you know, simple in order decoder. It just sort of deals with stuff as it gets to it. So if it gets to a branch, it stalls and waits a few cycles and then it continues. Nothing too fancy there. Yeah. At least when used, there's a decent amount of WEX magic going on. And a lot of conditional select operations there. But yeah, conditional select is another way of which it can avoid branches, so it can be all like, okay, compare and select which one of these values it wants based on the compare. No branch needed. It can also theoretically do WEX on the conditional select operations, but given in these cases each one has a individual compare behind it, yeah, it can't really do much with that. So then, well, not nearly as much WEXing going on here, and 16-bit ops are thrown in the mix, which basically means it's whenever you see 16-bit ops, it means the compiler is effectively dropped out of being able to use WEX right at that point. So, because when WEX is usable, yeah, when WEX is usable as far as the compiler is concerned, it will use only 32-bit encodings because, well, the encoding doesn't actually work with 16-bit ops as it is. Well, theoretically it would be possible to use 16-bit ones as operations as the lane 1 operation in WEX. This is not done currently and not currently allowed, but that would basically require multiple copies of the 16-bit encoder as well, probably to be used in roughly the same places as the 32-bit encoder, and so, but not necessarily wanting to have that many redundant encoders or decoders. Yeah. So it works. What does this say about this Kate situation? Well, the lion's share of the clock cycles, as it were, or about 7%, are going just into loading and storing double word values. So double word, pretty common. Branching, also pretty common. More branching. Unsigned double word. So yeah, these cases, decent chunk, probably a fair chunk of the clock cycle, or fair chunk of clock cycles, and then after that, well, pop and register moves. Register moves shouldn't be quite this common, but my compiler is kind of stupid, so yeah. So it does a lot more than it probably needs in an ideal situation, but oh well. Then add. Add is fun. And compare. More pushes. And add with carry. Add with carry isn't used much by normal scalar code, but it is used a lot by the color cell encoder, which runs quite a bit in terms of running something like Doom. Yeah. Then, yeah, quad workload store. That's different, but it's not nearly as high. And then, you know, you have unsigned byte and word loads here. So much fun. And constant and loading a constant value. So on. And it just sort of goes down the list for ever less common operations until it's all the crap that falls off the bottom. All the stuff with 0% is all the stuff that's not actually being used, at least for this program. So can be seen here that Doom apparently is having a decided lack of floating point stuff, but it's Doom. Also, I think it's being run in the E profile as well, which doesn't have the FPU enabled, so it's using software emulation. As noted elsewhere, yeah, there's a certain amount of artifacting due to Doom not using a full bitmap frame buffer, but instead using color cell. Slight artifacting right in this area due to color bleed over, due to the whole issue of it being color cell and basically ignoring color for most of the encoding process. The color cell encoder actually, yeah, only directly using the luma of the pixel for making its decisions and selecting the brightest and darkest pixels irrespective of their position in the color space. At least when done quickly, you wait a moment, it changes slightly. That's because for unchanging blocks, it will re-encode them with a slightly slower but slightly higher fidelity encoder, which does take color into account. This results in slight changes when moving, but yeah, where it will get yeah, when moving it will initially encode the color cells with a version of the encoder that entirely ignores color, and then when you stop moving and the pixels stop changing, it will re-encode it a short time later with a slightly more accurate color cell encoder that tries to take color into account to some extent. But yeah, the difference is isn't too significant because there's limits into what can actually be expressed via the color cell blocks. The reason it uses color cell is partly because the idea is it would try to represent the entire screen memory in block RAM, and initially I was trying to get all this stuff to work in either 16 or 32 KB. I ended up going with the 32 KB design because the 16K color cell just kind of looked like crap. But then again, it was all off effectively trying to fit something like a Doom or Quake into roughly about the same amount of display memory you would have on a CGA. So yeah, whereas as is, it tries to encode Doom into roughly half the display memory you would have on a VGA, or in some sense more equivalent to an EGA's amount of display memory. But admittedly, this looks a bit better quality-wise than it would look on something like an EGA, partly because it's, well, using color cell, which is essentially similar technology to what would be used on something like a Commodore or similar. So yeah, Commodore 64 style technology to encode Doom in, less video memory. Via the powers of color cell, it can also do full color graphics at 640 by 400 in 64K of memory, so it's a useful feature there. Full color at like a less visual fidelity than Doom here has, but technically a lot more color fidelity than you would get, say, from something like 16 color. But 640 by 400 by 16 color would itself normally require a full 128K of video RAM, but yeah, in this case, could get that using 64K and will have more colors, so not too bad. Oh yeah. So yeah, it's noted it's using basically, well, half the video RAM it would normally need on an FPGA or on a VGA to do the 320 by 200 by 256 color mode, which is what Doom would use, and only about a quarter as much as it would need for doing the 640 by 400 graphics. 640 by 480 would actually require a little bit more than 128K, so it's a trade-off. Well, so yeah, to do 640 by 480, you would, at 4 bits per pixel, you'd actually need closer to about 160K or so. So, yeah. Yeah, all the cost for those extra 80 scan lines. Similar for why one would do 320 by 200 rather than 320 by 240. It's like that 200 means you can, you know, have a convenient, like roughly power of 2 sides for your display memory, whereas those extra 40 or 80 scan lines mean it is not. So you need just that little bit extra to have those extra scan lines. Though like the advantage it does offer in that case is that you could have square pixels on a 4/3 display. So yeah. Though the emulator isn't entirely respective here of what it'll be like as is, because this emulator was assuming the former 100 megahertz clock speed, so that's what it tries to emulate, but because, yeah, the actual prototype is now limited to 50 megahertz, so maybe I will go and 50. What will 50 megahertz look like? Well, it'll be slower than 100 megahertz in any case, but the question is, will the frame rates look like something anyone would want to play? At least, like, yeah. Yeah, it's as noted. Kind of laggy. I'm pretty sure, that Doom was faster than this on the original 386s and 486s and stuff, but I've not actually figured out some of its magic. Well, besides this, potentially that it was running, that most of the inner part of its renderer was written in assembler or something, but yeah. Also, the logic currently disables the sound mixing for lower clock speeds, partly because the mixing logic isn't particularly efficient and ended up wasting a considerable number of clock cycles. Ended up wasting a considerable number of clock cycles at lower clock speeds, so yeah. Well, also the 386s and 486 PCs also had an advantage that they weren't sitting around trying to run a color cell encoder before being able to output their video. So the color cell encoding, yeah, that isn't free, but it works. I guess a testament to color cell encoding is that it's fast enough where it could be done in real time for something like Doom on a 50 megahertz processor, whereas try that with MPEG and yeah, that's not going to turn out well. So MPEG encoding's has a hard enough time happening in real time, even on modern, relatively fast processors, much less like, you know, something running at 50 megahertz. One could be all like, but what about all that WEX like stuff doing 3 operations per clock cycle and stuff? Why is Doom still laggy? And you know, yeah, that's one of those mysteries. I suspect because some amount of Doom isn't particularly optimizable via WEX. Basically, yeah, most of its inner rendering and stuff like that is loops that are going around copying memory around, and memory copying is one of those things that's mostly scalar. Well, and also, as if yet, the assembler for the color cell encoder hasn't been rewritten in a form where it can use WEX yet either, so the color cell encoder is for now still scalar code. At the assembler level, we do have to care a little bit about WEX versus scalar mode, but can be glossed over to some extent. Though, partial reason I've not done that yet is the assembler is written in a way to where it can't really actually utilize WEX all that efficiently, or all that effectively. Namely, as noted, those add with carry operations. Add with carry is effectively an operation that currently only really exists and is usable in lane 1 for now. Whereas given that's a decent chunk of what the color cell encoder is doing, well, that and compare operations which have the same basic restriction, so it's, yeah, I would need to figure out a good way to structure the color cell encoder where it's not using a bunch of conditional operations. Which is, well, an issue. Though the great irony is, with this, I still get like a lot less of a performance difference between Doom and Quake than I would on actual vintage 386 and 486 PCs, because here it's Doom is slightly laggy and Quake is, you know, a little bit more laggy, but Doom is laggy and Quake is more laggy, whereas like run that on a 486 and it was like Doom is fast, but Quake is a slideshow, at least on a DX, which actually had a floating point unit. But yeah, so DX66, welcome to slideshow Quake. But here, what's still pretty laggy, but it's maybe not quite as bad. As noted, the MIDI music still plays at these lower clock speeds, but And it's partly because, yeah, I was using a separate FM synth for like this stuff. The FM synth chip, or FM synth, like logic I did for the for both the emulator and like also for the processor core is, yeah, granted a bit simpler than something like a Yamaha chip, in that it's not doing the full like 9 channel or 8 channels of FM synth plus a percussive channel, but it's actually more of a 5-channel design, more sort of fancier than like the Commodore SID chip, but not quite as fancy as the actual Yamaha chip. And, you know, cuts corners in other areas as well, basically by using like triangle waves and similar rather than sine waves, because the sine waves aren't super cheap either. This map had actually one of the better songs in Doom, but kind of gets butchered by the like crappy FM synth, but yeah, or pseudo FM synth. The logic used by the emulator does actually try to roughly approximate both the math and the interfaces would be used in the Verilog module, so this isn't too far off from how it's likely to sound from the hardware version. Because, yeah, would be kind of pointless to go and have a fancy like or a fancy version of the FM synth in the emulator that actually goes fast, but or actually that actually sounds good, but you know, be limited to a crappy version in the Verilog implementation, which sounds like crap. So basically they both try to do roughly the same thing in roughly similar ways and stuff to try to give a more accurate approximation. Similarly, like similarly, the emulator also tries to roughly approximate things like cache behavior and similar as well. So yeah, color cell acting up can be seen quite visible there. So what is that blinking massive red and blue? What if we go over and look at it? So over here you can see it's this thing, and over looks reasonable enough up close, but then go away and it becomes quite a bit more obvious that this isn't using discrete pixels. Because yeah, the color information on here only exists on a per block basis, or for a block of pixels, so hence why as you get further away, it has a harder time approximating it accurately, and this and things that are happening in maybe only a few pixels affect the color for the entire pixel block and result in, pretty obvious screw up. But for the most part, looks actually surprisingly reasonable. Also, partial reason the sound doesn't work in this mode is, well, due to CPU cost, but yeah, partly because of the mixer code, and also, yeah, because I'm not sure how it worked in the original Doom, and they just sort of ripped all that stuff out of the open source version, so I had to recreate it, and had just used some logic which did some quick and dirty but not good for this case stuff of, using floating point math for the sound mixing, which is a problem if you're dealing with potential FPU emulation, so I'd have to rewrite that part. And also, there's this ugly situation known as it doesn't use a PCM audio buffer either, because that would take block RAM, or take a lot of block RAM, so it just sort of does this cheap compromise option of using sort of a small block 80 PCM, and so whenever it sends audio to the audio output, it has to 80 PCM encode it, and that's not entirely free either. For for things like Doom and stuff, for things like Doom and similar, at lower clock speeds like 25 or 50 megahertz or similar, that 80 PCM encoding and like sound mixing was actually being a considerable chunk of the total clock cycles, or total clock cycle budget, so it was causing the performance to be pretty much terrible, so I disabled it. The better future case option would be like, maybe make that logic or that code more efficient so that it can still have sound, which is probably what I'll end up doing at some point. But as can be noted, one can wonder, well, if it's outputting color cell and stuff and Doom doesn't directly render as color cell, what happens? Well, it actually renders first into a frame buffer and in RAM, and then it invokes the color cell encoder afterwards to be all like, okay, encode this image into its color cell form and shove it out to the graphics hardware, and it does so every frame. The result is, the result is this. Admittedly, I'm not actually sure why more people don't, use color cell encoders for real-time video encoding or similar, because, that is, well, its quality is kind of crap and its bit rate is kind of crap. it is quite a bit cheaper than, like, you know, pretty much most other options for real-time video encoding. So as this can be taken partly as evidence, like, you know, this is happening real time on like what would be essentially a 50 megahertz processor, and without even being able to use its like WEX capabilities or anything. So it's, you know, just straight up scalar code, and it still works. So enough for now. And what does this say? Now, most of the memory, or most of the cycles are still memory load store. Not too surprising. And add with carry for color cell is now, yeah, so the color cell encoding is, well, a pretty big chunk of the total. And yeah, roughly 11% of the cycles are being spent in L1 cache misses. Well, emulated, of course, but you get the idea. And because the L1 is small, and yeah, about 17% is L2 misses. I think it's assuming a 32K L2 still for this. I'd have to check on that. So about 28% of the total clock cycles are, you know, just spent in cache misses, which could maybe be improved, but yeah. And so about 40% is the mem operations themselves, which this includes mem operations that, like, you know, don't have cache misses. So what is this? Okay, so it's 65% of the total is memory. Just memory loads and stores. So can be noted, this stuff is arguably more memory bound than it is like more memory bound than it is like C or ILP bound, but reasonable enough. The gains from WEX won't exactly be all that large for a memory bound program, so but it's a trade-off. Also in the case of my prototypes, it seems to be that it's cheaper to like you know, just add WEX and similar than it is to try to make the memory subsystem not be slow, but because yeah, as noted, yeah, memory subsystem is kind of expensive. The memory subsystem is actually almost the most expensive part, so so not looking at FP, so mem L1, what does, so the L1 D cache, well, almost 4,000 LUTs that are elements just there, and about another 1,000 for the I cache, or for the L1 I cache. What about L2? Yeah. So not too bad, and it's only like 400 for that, and another 300 for the ROM. So yeah. you know, still kind of expensive in any case. But this is granted where a decent chunk of the block RAMs are going. So yeah, but you know, you see some block RAMs here, but a whole lot of flip-flops and LUTs, more flip-flops. Yeah. And carry units, but the cache doesn't do huge amounts of arithmetic, apart from mostly a few simple address calculations and stuff, but yeah. What about this VGA module? 400, another 1,000. So this is the frame buffer's memory module, and this is the VGA output driver, and another 1,000 for the color cell, or for the color cell decoder module. Oh, color cell decoding isn't free, but the color cell modules also deal with like text mode and similar as well, so it has the capability of text mode. And in the 320 by 200 mode, it's also effectively operating in a 40 by 25 text mode at the same time. So it's just functions as either a text mode or a graphics mode, depending on what you stick in the color cells. With, as can be noted, effectively 8 by 8 color cells. In for graphics and stuff, those color cells can be split into 4 by 4 subcells. So yeah, so a 4 by 4 subcell for each color pair plus stuff. Yeah, 8 by 8 for the total number of pixels. In the 640 by 400 mode, using 64K, it's like also pretty similar, you know, with 64 bits for the pixel data and the remaining bits mostly for the color cells, or for the color cell colors. Actually, wait, no, it's 128 bits for the pixel data in the 640 by 400 mode. That's yeah, pretty much. So yeah, those 128 bits for pixel data can be used to encode like 8 by 8 pixels at 2 bits per pixel, which is what things like Doom and similar were using, but it can also encode 8 by 16 pixels at 1 bit per pixel, which is useful for higher resolution and stuff at used for higher resolution, but but like at with less interpolation, since you can only do select between the two endpoints rather than like, you know, select between intermediate values of those endpoints. But it can be useful. There's also an 80 by 25 mode, which doubles the number of horizontal columns but at the expense. Yeah. Actually, wait, yeah. And you gotta do the 640 by 480 mode, or 400 mode, you would be using it in 80 column mode. So 40 column gives 320, 80 column gives 640. But yeah, more or less. The color cell display would probably be its own topic in its own right, but yeah. So good old instruction listing, showing which all instructions exist. As no and be noted, the characters or the letters which are uppercase and numbers and stuff, if they fall within a range that's valid or a valid hexadecimal value, then that's how they're interpreted. So the F2 or F2 in uppercase and the 9 represent the literal hexadecimal bits, whereas N and M in this case mean the register ports. But yeah, that's a convention issue, and not to be confused with what's being used in the core. So N is generally the destination, so N maps the same as it maps to the NMO ports as it would the thing I mentioned earlier, whereas M generally corresponds to the S port, or the S or U port, or X. Yeah. Then the displacement. A displacement or immediate value would generally go in the T or V port. That's how it works. Jump compare doesn't exist on my current core prototype, but yeah, it's another extension, just not in the ERF profiles. Also, not currently done because not currently being prioritized, because even if they were added to the to the CPU core, they wouldn't give much performance advantage, since the timing plus jump logic would take more than a single cycle. So yeah, as is, it takes 2 cycles to perform a compare and another cycle to do a jump, so you wouldn't gain much by having a combined instruction. Combined jump and compare makes sense either if you're dealing with a fixed length 32-bit encodings, which you know that you don't have to spend 8 bytes to do a branch, which is one possibility, but in this case I have 16-bit operations that can do the same basic thing, so it doesn't save much there, and won't save much in terms of cycles if you need 2 cycles to do a compare. It makes more sense if you could theoretically, you know, save the cycles by having like a compare that takes less than a cycle and a branch that also can be shoved into the same cycle as that compare. But since that's not how it works in this case, doesn't save much. So that's why I consider it an optional feature, which is why I put what I mean when I put the name inside of parentheses like this. So parentheses feature name optional feature. Hence similarly for these FPU loads or stores. These are ones that would use actual dedicated floating point registers, so they're optional because actual FPU as opposed to GFP, which is its own thing. Similarly, floating point divide, it's another extension. Does GFP have FDiv? No. Does the main floating point unit have FDiv? Potentially. It could have FDiv. Or it could just, you know, do it in software, which is currently how it's done. So GFP ops are by themselves. No FDiv for GFP because GFP doesn't do divide. Well, more or less at all. And yeah, packed conditional select for the GSP. So the normal select or conditional select, you know, selects the whole word at a time. So you can select which of these versions of the register you want based on a single bit. The packed select like will select for each half of the register. So you can potentially select the high half based on one bit and the low half based on the other bit. There's actually packed compare ops. So swap and copy. Yeah, that's how shuffles are currently implemented. To be decided whether to add an actual shuffle op. I've considered it, but not done so yet. While it wouldn't be free, would be potentially useful if, you know, simd is actually used for something. So some more GFP ops. So these do. So there's a big chunk of operations for the conversion, or type conversions, and negate and absolute, and compare equal and compare greater than. With the add, subtract, multiply from earlier, that is basically GFP. Not a whole lot else is done by GFP besides, you know, conversions, then compares, and also add, subtract, multiply. Interestingly enough, just this much is enough to regain most of the performance you'd have with a full floating point unit. So all that extra fancy stuff like transcendental functions and whatever doesn't really actually buy that much. So yeah. Well, even then on x86, those things are like, you know, few hundred or several hundred cycles now, so it's all like not like they're really gaining, not like you're really gaining a whole lot of performance by being able to, invoke sign as a CPU instruction as opposed to just doing it in software or something, but yeah. So when in doubt, do it in software. Kind of surprisingly effective in this case. Oh, what is this? This is the GSV ops, the main blocks. So you got your packed add and subtract, and add with carry and subtract with borrow. Then the GSVF features, which are debatable. Some packed moves, more packed moves, selects and compares, and some format conversions. So what these do is, sign or 0 extend byte to words, low, and you word to double word, like keeping them in the low position. Then you can also convert byte to word or word to double word with duplication of the value twice, or just keeping it in high position and copying zeros into the low bits. And similarly, you can go the other way, narrowing. So word to byte, double word to word, and so on. Then word to byte and double word to word without signer unset. The difference here for GSV ops is, so these ones are basically take the place of saturating arithmetic. So when you go from word to byte with like a sign, with these ones, it'll basically clamp the value to the target range and stuff during conversion. One can debate, well, why not just have full saturating arithmetic if you're going to have, saturation on convert bits? So, like, well, this still works out cheaper, I think. So yeah, no need to have alternate saturation modes for your packed add and so on when you can, just or when you can handle it on convert. And like this, it's mostly some special case range check logic, to detect if it's not in byte range, or not in the byte range, and then some logic for, well, okay, if it's not in byte range, then do we stick in OXFF or do we stick in 0? And yeah, timing is easier when it's by itself. So, and then we have low and high versions, because do we want to keep the low bits or the high bits? And probably sufficient for most uses. And GSV is takes up, like, 2 blocks, or 2 of these blocks worth of instructions, as opposed to like, the much longer listing you'd have with something like MMX or SSE. So yeah. But yeah, serves a functionally similar role to MMX in this case, but without some of the drawbacks of MMX. Though, admittedly, GSV is still largely unused at this point as well, because yeah, C doesn't map conveniently to sim types, and even then it's yeah, and as such it's considered an optional feature because yeah, it's considered an optional feature because with cheap core you might not need this. (16-bit) land. So that not the 9 block fits the entire FPU in it, which is not used in these profiles, but still like fits the entire FPU into effectively about the same space or same encoding space as the original Super H FPU, so not too horrible. And it does it without crappy mode twiddling stuff to deal with single and double cases, because it uses the same encoding space and it does both single and double without needing to mode change. So better design in my opinion. And also easier to make it past timing, which was basically something that wasn't going so easily with the Super H style design. And 16-bit operations for GFP, so you have add, subtract, multiply, the single to double and double to single conversions, and the compares. These are the most commonly used operations from GFP, so it made sense to have them as 16-bit forms. And the 7 block is still unused because even with all this crap going on, I still not managed to run out of encoding space, so or entirely run out of encoding space in 16-bit land, so that itself is a slight advantage over Super H's, because with my original BJX2 design, I was having to basically try to shove everything into little corners in terms of encoding, and that was kind of a pain. Here the encoding is a little more consistent, and I'm not entirely out of encoding space, so I still have like a full 12-bit block unused, so improvement. So we can load 12-bit immediates into DLR, so that's the amazing 12-bit or constant load thing, and yeah. And add or load 8-bit immediates into, well, any of the arbitrary low 16 registers. The high 16 registers, of course, have these much more limited 4-bit immediates, but yeah, the loading loading a loading or adding a 4-bit immediate at least isn't entirely useless, so that's partly what justifies these existing. It'll load or store stack relative. One could argue that this case and this case, well, also this case and this case are kind of, actually wait, those wouldn't apply. So this case and this case here, namely the load and store double word sign extending with a 4-bit immediate, is almost redundant with the DIM3 block, or disk 3, 3-bit displacement block for move-L, but they're not quite entirely redundant because it has, one more bit on the displacement, and also one more bit on the displacement, and also can deal with all of the registers, whereas this can only deal with the first 16 and only with sign extending, in a few and certain 0 extending special cases. So because the displacement of 0 was redundant with with the ones that didn't use a displacement, the ones with a displacement 0 cases were reused as 0 extending loads for in case of double word. Here's the 0 extending byte and word operations. 0 extending loads didn't exist in Super H, so this is another slight advantage BJX2 has. Namely, it can do this a little bit cheaper without needing an explicit sign or explicit 0 extension operation, which is useful because things like unsigned byte is actually semi-common, so single register ops generally implicitly have access to all 32 registers because of the encoding. In terms of 16-bit land, only 8-bit displacements exist for branches, but I had earlier done a mock-up of what if I had a 12-bit branch displacement in 16-bit land, but I determined through testing that it wouldn't have actually made enough difference to be worthwhile, so I didn't bother, and I've left that encoding space probably for something else. It's as one would think, well, yeah, what about all those cases where you need to branch further than plus minus 256 bytes, but you don't want to spend 4 bytes or spend 4 bytes on the branch you'd need for a 20-bit displacement. You could have a 16-bit branch that does a bit more, 4K or plus minus 4K, but seems like it would be a lot surprisingly enough, the actual sliver of branches that fit in that range is not that huge. Because the vast bulk of branches that are within a function, like, fall within this small 8-bit range. So the 8-bit branch is sufficient for yeah, it's sufficient for a majority of intra function branches. Well, except when it's not, but we can't do much about stuff like this. Partly because from a mix of compiler being stupid and or it being Wex, but well, not Wex because Wex doesn't apply to branches. But yeah, but intra function, yeah, most of the time, like a direct branch is sufficient, or an 8-bit branch is sufficient. Again, another case of except when the compiler is being stupid. Yeah, either way the case was, experimentally, the 12-bit branches didn't really save that much in terms of total code size, so I didn't bother with them. Sort of, you know, you have a rapid fall off between, you know, extremely short branches, and when you get to ranges where you might need a 12-bit branch, so then it falls off pretty far by that point, and then after that it picks up a bit where you would need something bigger, like a 16-bit branch, or 16 or 20-bit branch. So, and it suddenly picks back up again for a little bit, but at that point, a 12-bit branch isn't going to do much good. So there's this sliver of ranges for where you might need a 12-bit intra-function branch, but it's not that big of a sliver, so it doesn't save too that much. Or at least that's my justification. So yeah. I'm not just designing all this stuff willy-nilly, but a lot of the design for this instruction set is based to some extent on empirical testing. Though granted, partly it's empirical testing mostly with Doom and Quake and Stimor, but just pretend that Doom and Quake and other similar code is representative of programs as a whole. You know, and pretend that they actually performed not crappy. So how well is Quake going to hold up at 50 megahertz? And not well, but I think this is my emulator's Wexlinting. In this case, the operations look like they should be fine, so I suspect what's going on here is basically previously the compiler was failing to so so previously the my compiler is like failing to emit the WexMD instruction, which is the one that specifies which mode we're expecting for like at Wex to operate. But the current emulator's linting, if the mode isn't set but it encounters Wex sequences, then it's not happy about it and will explicitly transform the instruction into a break instruction, so that it can lint it. It's kind of where I'm going in terms of like actually trying to verify that my compiler is outputting valid Wex sequences, because the emulator at least has a chance of doing something sane here. So will Quake work now that I've rebuilt it? Okay. Okay, so Quake is failing to disable console printing. So Quake is failing to disable console printing while running and stuff. So that's what some of that's about. Because it's the color cell console and stuff, printing will interfere with the graphics output. But yeah. Crap, I have no idea about volume. So I'm going to assume I can still be heard over this, but yeah. Okay, so I've made it a little less noisy. But yeah, that was something I did add to Doom, was some logic to tell the console printing to not do its thing if, yeah, to tell it to not do its thing if, graphics were being drawn, but, haven't added the logic to Quake to tell it not, or to disable console output yet. So that's what's going on there. So now whenever it tries to print the console, it interferes with the color self frame buffer by, you know, trying to scroll it and draw text and crap. Which is admittedly kind of really annoying if you're dealing with something, because in this case you don't want it trying to draw to the console and scroll things and stuff. And Quake's performance at 50 megahertz is, well, decidedly bad, but you know, I sort of somehow, from my vague memory, this is still possibly better than it was, you know, trying to run this crap on a 486, so yeah. And for what it's worth, yeah, the capabilities, of the BJX2 core won't be that much different, or it won't be that much different than something partway between a 486 and a Pentium 1 anyways, so yeah, it's kind of reasonable that it performs roughly on par with if you took a Pentium 1 and seriously downclocked it. Granted, on actual hardware probably would at least hope for performance better than this, but yeah. enough of this because I'm giving myself motion sickness trying to deal with that. But yeah. So, floating point divide function, spans drawing function. So yeah, there is some WEX going on. I haven't set it to doing 3 wide yet, but yeah, or I haven't set it to doing 3 wide when building Quake, so it's only doing 2 wide for now, but yeah. But still. And this of course is scalar code, but then again, GFP is still lane 1 only, so trying to use WEX for the floating point divide function, but divide logic wouldn't actually save that much as it is. And Quake is similarly dominated mostly by load stores, but also floating point multiply gets its share in as well. And it is spending roughly about 60% of its total clock cycles in memory load and store. So, kind of expensive. Possibly Quake could be a little bit faster if it were if it had an assembler, or actually a renderer core that was written in assembler like is on the case on x86, but it basically works just sort of using a plain C version of the renderer. So not too much notable. So at least parts of the renderer are using WEX. So it's not going entirely to waste. Well, except that part's all scalar. So here we can see a predicated op, or predicated operations as noted by the question mark and the F, which, so you got a constant load and a memory store and a negation, and yeah, so compares something to 0, and if something is if something's less than 0, then what it will do is it will do a few instructions. But this is generally how conditional op, or how predicated ops end up being used, because if you have just a few instructions, it works out cheaper to predicate them and treat them as nops here than it would be to do a branch over them. So that's why predicated ops exist and the cases where they're used. For much longer than a few instructions, though, for much longer than a few instructions, it becomes cheaper to just branch over the operations rather than predicating them, So they're only really useful for small blocks. The compiler actually will count how many, or count the complexity of the block and expressions it sees there, and refuse to use a predicated form of the if branch if it exceeds the limit. So that basically works in trying to keep it efficient. Yeah, it does save some cycles for these really small branches. Like, yeah, if this value is equal to 0, then set it to 1. Total cost of doing it this way, about 2 cycles. So yeah, about 2 cycles. In this case, for the compare equal, or the 32-bit compare equal, and for the load a constant if it's true. If I were to do this via a branch, it would cost closer to closer to about 6 cycles overall. So so basically 2 cycles for the operation and maybe about another 4 cycles for the branch. So, and oh yeah, the elusive Lee instruction. So here loads a constant and it does a GBR relative GBR relative Lee and gets a pointer to somewhere in the data section. So that's what that does. And then does a relative load relative to that pointer. So probably here we're looking at an array of unsigned double word values, and it for whatever reason decided to load a pointer first and then access it relative to that pointer. In this case, we could have technically skipped this Lee and just done the load directly, but and also the sign extension is completely pointless, but yeah. Technically, we don't actually need this in the 32-bit address modes anyway, since any bits above the 32-bit mark are more or less completely irrelevant for memory load and store displacements. This here might possibly matter. It might possibly matter if we were dealing with it might possibly matter if we were dealing with 48-bit addressing, but not really. If we look at this operation, which is where it came from, so load 63 and this register gets 63 and use it as an index. Of course, we can see here we don't need to extend it because, well, it's ANDed by 63, so its range is pretty limited, but but for that we'd require the compiler to actually be smart, which is kind of not sometimes. So yeah, this whole sequence could be made a bit shorter if the compiler were a little smarter. But that's what I'm dealing with here is my compiler. It's not smart, but it's maybe kind of acceptable. Sometimes you also catch a glimpse of the cases where the compiler, like, stores to a location and then from a register, and then immediately reloads it from that same location, which is again kind of pointless, but it's another one of those cases of making it not do that would require the compiler to be smart. But it is at least smart enough to where it's not doing that pretty much continuously. Like, it will actually, for the most part, be able to keep things in registers. So, yeah, but just not consistently. So it's better than, say, like compiling in debug mode with something like GCC or similar, but not quite as smart as even as its level 1 optimizations, because even its GCC's level optimizations or level 1 optimizations still sort of beat beat my compiler, which is BGBCC. But yeah. Unsigned multiply of quad word. This also exists because of the lack of or because the multiplier only does 32 bits. So we end up having to just do a bunch of twiddly to get a 64-bit out, or to do quad word multiply from 32-bit multipliers. So a lot of shifting and adding. And as we can see, when it's actually doing the dump, the majority of this stuff in this case is scalar code, not even using WEX. Though that does sort of make me think, yeah, is Quake being compiled for optimization? So BJX2F. So F profile. But it is being compiled in its default mode. So what if we enable it? Yeah. So full optimization, or faster optimization, so optimize for speed rather than optimize for default, and turn on 3 wide WEX. And then we can see if that makes any real observable difference in the performance of Quake. Or if it just results in it exploding immediately on startup or something, but yeah, it's always a risk with this as well. So it's maybe a little bit faster, but I can't tell. It's still pretty laggy. So an epic, 2 frames per second. That is, well, pretty much dismal, but yeah. So unsurprisingly, still scalar there. A little bit of WEX going on in these renderer functions occasionally. And a 3 wide operation right there. Not a whole lot of 3 wide operations for WEX in general, but it's something. If a person wants to like to write their own assembler, they can, use a lot more WEX, but yeah. Of course, none here, but this is quite heavy with memory loads and stores, and tight sequences of instructions which depend on each other, so not a whole lot of WEX magic's going to happen in that case, so yeah. No, we can see that, at least in this backtrace section, there's a bit more going on in terms of WEX optimizations, but yeah. and I've been talking for 4 hours, so I'm going to call it an end for now. After some final tweaking.